Hello and welcome to this video on the subject of superheating. On this first slide we can see two heating scenarios. In the top half we have heat going into a metal lattice. The output is shown on the right hand side. So the amount of heat going in is at the melting point, Tm. No surprise, the metal melts. The second heating scenario we have in the bottom half, again, heat is going into the metal lattice. This time though, note that the temperature is 2 times or just over 2 times the melting point. Now, in this particular case, the output, as you can see, the metal has not melted and it has maintained its structural fabric. However, of course, the ions are going to oscillate within the metal, and I've attempted to show that by blurring the image slightly. Now, the scenario in the bottom half of this image is something which we call, and the subject of this video, superheating. So the question arises, what exactly is superheating? Well, the answer is partly given on this slide and in the following slides. Now, on this slide we have a graph, or perhaps 3 graphs if you like. The vertical axis on the graph is entropy. The horizontal axis on the graph is the temperature of the metal lattice. Now, in this particular case, the metal has become gold. So in other words, the plots shown on these axes are for gold. There are 3 plots shown on the axes, and I'll go through each of them in turn. The green plot shows the scenario that was shown in the top half of the previous slide. In other words, it's a simple case of where gold melts. The blue plot is refers to the bottom half of the previous slide, and in other words, it is superheating. Now, the purple plot also shows superheating. So we have 2 states of superheating shown on this graph. So what's the difference between the 2 plots? The blue plot shows early work that was done on superheating, and the purple plot shows the most recent work on superheating and the work which is covered and described in this video. The earlier work on superheating, as I mentioned, as shown in the blue plot, theorized that at a particular temperature point, a particular incident would occur. Now, that point is shown on this graph as the vertical dashed red line. The people who worked on this earlier form of superheating called this point entropy catastrophe. Now, these are emotive words, but given what they expected to happen after this point, they are perhaps justified. What they predicted was that above this particular temperature, which is 4 times the melting point for gold, the metal would undergo an uncontrolled expansion, and hence we get this sort of exponential part of the curve. However, the earlier work was only able to achieve a maximum temperature of twice the melting point, and they never achieved this 4 times the melting point. Now, this was a technology problem at the time. In other words, the technology at the time wasn't available to probe a temperature level of 4 times the melting point. The current work, though, did manage to probe this particular point. In fact, they went way beyond it, as we will see. So on this slide, which is just text, the definition of superheating is covered in more detail. So what is superheating? Well, we've seen that it's achieving temperatures above the melting point such that the metal, or gold in this case, doesn't melt. Now, it's not just a simple case of getting trying to get the gold up to a particular temperature above the melting point by just supplying a continuous supply of heat. The important point is that the heat has to be supplied at a particular rate. So what is that heating rate? Well, the heat has to be supplied at a rate which is greater than the rate at which the gold lattice can expand. The earlier work on superheating, as can be seen in the second paragraph, could only achieve heating rates of 10 to the 14 Kelvin per second. The more recent work covered in this video has, as I've mentioned, managed to achieve much higher heating rates, and how they manage to achieve that is the subject of the next slide. So, how did the most recent work manage to achieve higher heating rates than the earlier work? Well, they used X-rays, and the X-ray source they used was the LINAC coherent light source. Using that source, they managed to achieve heating rates in excess of 6 times 10 to the 15 Kelvin per second. This high heating rate managed to achieve a temperature of gold at approximately 19,000 Kelvin. The energy of the X-rays that they were using was just over 7,400 electron volts, and they monitored the temperature of the metal by detecting scattered X-rays. The energy of the scattered X-rays was a mere, compared to the energy of the source, 47 milli-electron volts. How they measured and analysed the scattered X-rays is the topic of the next slide. So in this slide we can see the ions of the gold scattering the X-ray photons. Now, the as shown, the X-ray photons are scattered at different wavelengths. The type of scattering that goes on within the gold is inelastic scattering. The scattered X-rays were measured by a very high precision spectrometer, which I've just shown as a typical spectrometer output in the top right hand corner. After the X-rays have been scattered, they have a tendency to be Doppler shifted, hence the wavelength changes I mentioned a few seconds ago. However, they also eventually settle down into a Gaussian profile, which is shown in the bottom right hand corner of this slide. Now, this profile is of central importance to the work covered or described in this video, because at the full width half maximum point, the energy across that particular point correlates exactly with the temperature of the gold. So, as can be seen under the graph, the delta E is about 121 milli-electron volts, and this correlates to 19,000 degrees Kelvin. So, to summarize the work discussed in this video, the group managed to achieve superheating using X-rays. Those X-rays were injected into the metal at very high transfer rates, and furthermore they could directly get the temperature from analysing the scattered X-rays. Now, the work that I have covered in this video is summarised in a paper, and the link to that paper I've put in the description below this video. It's a Nature paper. If you have further interest in this, then try and read the paper. I think you'll find it very interesting. So anyway, thank you for watching this video, and more videos will be coming soon.